Okay, please start.
Okay, very good. Thanks, Janet, for the introduction and invitation to give this talk. Today, I'm very happy to tell you about two papers that appeared in the course of the past half year, written in collaboration with Hugo Camargo, who's my PhD student, Lucas Hakel, who's now in Australia, Alexander Yan, who's now at Caltech, and Bennett Vint, who's at Imperial College, as well as with Tadashi Takanagi, who is with us on the first work. Um, so let me start with the introduction, and I should also say that today on this special occasion, I'm wearing a jacket that I bought in Shanghai during my visit in 2018 that I like a lot. It was a very nice experience to be there, and I'm sorry I could not make it in person this time. So let me put everyone on the same footing. And of course, if you have any questions, please interrupt me because I mean it's nice to have these virtual talks that are a bit interactive. The big picture for me stems from recognition that much of quantum gravity progress in the course of the past decade occurred in ADS CFT and not using any tools, but actually using holographic entanglement entropy and its refinements. So if this is the picture of an ADS space, you can think of it literally as ADS3 space that it depicts. And it's an empty space, so it corresponds to vacuum ADS spacetime. We pick a canonical time slice on the boundary of this spacetime where a dual holographic conformal field theory lives. This defines a state in this holographic conformal field theory, and this state is going to be the vacuum state. And what we do is we bipartition the state into subregion A, say in this case an interval, and its complement, that in this case is going to be another interval. Then it turns out that the area of the minimal surface, of codimension 2 minimal surface in the bulk, so in this case the area of this, so the length of the segment measured in natural units, reflects is nothing else than a fundamental entropy of a reduced density matrix in A. So it's nothing else than an entanglement entropy. So this is the proposal that appeared in 2006 by Ryu and Takanagi, that was later in 2013 proven by Malocera and Lekowicz, then was used in many instances of studies of quantum gravity. And if one goes back to 2006 and tries to think about the history of this discovery, the fact that Ryu and Takanagi were able to, come up with this idea in a fully convincing way happened because prior to 2006, already many things were known about entanglement entropy in quantum field theory or conformal field theory. That is, before 2006, we already knew that the entanglement entropy in quantum field theory obeys the area law, right? That it diverges as the area of the entangling surface measured in the UV cutoff. Then in 1+1 dimension, this area law gets replaced by the logarithmic scaling of the entanglement entropy with the size of the subsystem. So this L is the size of this interval, roughly speaking. And this is a universal formula that is the same in any 1+1 dimensional conformal field theory and is basically expressed in terms of a central charge C. And then in 1+1 dimensional conformal field theories, one can very effectively use replica trick to calculate entanglement entropy. And in particular, this is what was used by Maldacena and Lekowicz to prove Ryu-Takanagi conjecture, etc., etc. So this is the entanglement entropy. It's by now rather well studied and I would say well understood, both on the gravity side and in conformal field theory side. Of course, it's a subject of also of ongoing research, so there are still many interesting research questions that are left unanswered. However, this talk is not really about entanglement and about holographic entanglement entropy. It's about something else. And the segue to whatever I have to tell you comes from the fact that more recently, in the course of the past several years, a few bulk quantities were conjectured to correspond to quantum information notions not studied in quantum field theories, not studied till at least the moment of these proposals in quantum field theories and CFTs. So the three quantities that I have in mind are complexity, about which I talked at Fudan in March 2018 and November 2020 at the conference that you hosted. And the two remaining ones that I have in mind are entanglement of purification and reflected entropy. And these are the subject of this particular seminar. So yeah, so the story of entanglement of purification and reflected entropy in the context of quantum field theory arises directly motivated from holography, and this is basically going to be my last holographic transparency, and in the following I'll just move to the quantum field theory side. So so this is the picture of a constant time slice of 80 anti-de Sitter spacetime. It's a hyperbolic disk. Imagine that on this hyperbolic disk on the boundary you pick now not a single interval but two intervals, right? So this is the interval A and this is the interval B. When these intervals are large enough, the Rita-Kanagi surfaces connect them like this. So the magenta curves are Rita-Kanagi surfaces. And you know, if you compute the area of these Rita-Kanagi surfaces, so in this case the length, then what you're calculating is basically entanglement entropy of the union A union B. And one UV finite quantity that you can consider that is composed from S A union B is the mutual information that is defined as entanglement entropy of A plus entanglement entropy of B minus entanglement entropy of A union B, right? It's a UV finite quantity, that is, it doesn't depend on the UV regulator. And since basically all these Rita-Kanagi surfaces are known analytically, then you can calculate it and you're going to have an analytic understanding of how it looks like in holography. And in certain quantum field theories, you can also calculate it, and you can have an expression for it. Now, this is an old story. I mean, like the mutual information has been considered in mutual information has been considered in holography from very early on, like soon after the original proposal by Ryu and Takayanagi. However, what appeared in 2017 and later was reconsidered in 2018 is another quantity that is a UV finite, that is basically nothing else than an entanglement wedge cross section. So this region here is entanglement wedge of A union B, and what one can do is one can calculate basically the distance here in this case between these two Rita-Kanagi surfaces. That is, one can consider pairwisely, you know, like distance between all the points on this surface and all the points on that Rita-Kanagi surface, right? And the minimum of this distance is going to be the distance of this between these two Rita-Kanagi surfaces, and it's precisely given by this cyan interval, and the length of this the Bekenstein-Hawking entropy of the cyan region here is basically the so-called entanglement wedge cross section. No? So it's a geometric quantity that we can consider whenever you have, you know, two Rita-Kanagi surfaces. And of course, the interesting thing to do is to ask a question: if this is a geometric quantity on the gravity side of ADS-CFT correspondent, what does it correspond to in a dual quantum field theory? And in 2017, two papers that were very close by in time, one by Takayanagi and Umemoto, and the other one by the group centered in Maryland in the States, proposed that entanglement wedge cross-section is related to the quantum information quantity that is called entanglement of purification. And in a later paper, there is a competing proposal put forward by Dutta and Faulkner in 2018, in which they provide evidence that entanglement wedge cross-section is actually one half of another quantity that is called reflected entropy, that is closely related to entanglement of purification, but a priori is distinct, right? So, so this is all that I have to tell you about holography. the take-home message from this slide is that there is a good reason to understand entanglement of purification and reflected entropy in quantum field theories in general, in particular in conformal field theories, because actually at the moment that these conjectures were made, very little was known about what these quantities are. And please don't worry if you have not heard these names, because like in the subsequent slides, I will try to rather precisely explain what these quantities really are in terms of entanglement entropy, okay? But the punchline from this is that we want to use these works as a motivation to understand entanglement of purification and reflected entropy in quantum field theory using some exploratory calculations.
Oh, sorry. Can I just ask a quick question? So, what Dutter and Faulkner has shown is that is it that it is they prove that the entanglement cross section is equals. Is that a proposal or a proof that somehow these two quantities are the same? That entanglement of purification is the same as half reflected entropy in holographic theories, or is that an alternative proposal?
No, I would say it's an alternative proposal that does not disprove the other proposal, because it's possible that there are states in which these two quantities are related. So entanglement of purification and reflected entropy are related by a factor of 2. And this is hard to disprove. So in particular, there are calculations by that I will show later by Tadashi Takanagi and collaborators, in which they are able to calculate entanglement of purification in quantum field theory and compare it with holography, noting agreement with their proposal.
Oh, okay.
So it's not a priori excluded that both proposals are right. However, the relation that this imposes between them is fulfilled only in some special class of states in holographic quantum field theories.
Okay, thank you.
Yeah, thank you for the question. And also, like, if, as I said earlier, if anybody has any questions, please go ahead and ask. Good. So there's entanglement of purification. There is a reflected entropy. So like in the following, I guess, 2 slides, I want to tell you what they are, so that you have a better understanding of what I want to do next. So the crucial thing is that reflected entropy and entanglement of purifications are quantities that involve purifications. And purifications are nothing else than embedding mixed states as obtained from pure states in an enlarged Hilbert space via partial trace, right? So if you go back to this particular example, we consider a mixed state that is defined by the reduced density matrix in AB, and one purification of such a reduced density matrix in AB is going to be the original vacuum state. But it's not the only purification, right? And in this business of purifications, you have to be a bit more open-minded, right? And you have to allow also for other purifications, not necessarily the one from which you obtain the density matrices. So one example, and like this is going to be the example that I will stick to in the next transparency as well, is a thermal state, right? So if somebody gives you a thermal state, then your natural instinct would be to purify it to a thermophile double state. So if you have not heard about thermophile double state, the idea is that if somebody gives us a thermal state in in some quantum mechanical system, for example, quantum field theory, or a quantum mechanical system, I mean any quantum mechanical system, in order to define a thermophile double state, we consider 2 copies of such a system. So we can denote like these copies by a left and right copy for the reasons that are going to be apparent in a sec. And the thermophile double state is a particular entangled state between these 2 copies of the system, in which the entangling pattern goes through energy eigenstates. So we are supposed to perform a sum over all energy eigenstates in the system, and we're entangling, basically we're entangling the two systems by summing over all energy eigenstates, and in a sum, like each term is the energy eigenstate in one system, tensor energy eigenstate in the other system, right? And the relative weighting between these different energy eigenstates is given by the square root of the Boltzmann factor, and then you can reinstate normalization if you want, right? And now, when you define such a pure state in large Hilbert space, that is a Hilbert space that's a tensor product, that is basically like a squared tensor product of the original system, then the thermal density matrix arises as a partial trace over one of the copies, right? So if you take the state and you take a partial trace over the left system or right system, what you end up with is the original thermal state. And now I would probably not be talking about it if not that in holography, this thermophile double state has a very beautiful and very straightforward manifestation, which is the maximally extended ADS black hole solution, and this is something that we know due to Maldacena. So this is the maximally extended ADS structures black hole solution. There are two boundaries: the right boundary, the left boundary. Right? There are future singularity, past singularity, the horizons, and if we pick a time slice, now there are two boundaries, so we have to pick like two time slices on the boundary, like on the right boundary and the left boundary. Then it turns out that such a time slice corresponds to the thermophile double state involving left and right copy of a holographic CFT. So this is very general what I described, because a direct analog of a thermophile double state can be constructed for any density matrix, right? So if you look at the definition of the thermophile double state, you see here is that the eigenvalues of the thermal density matrix are basically Boltzmann weights up to normalization, right? And the thermophile double state is a sum over square roots of these eigenvalues, right? So what I'm saying is that if somebody gives you a density matrix, not necessarily viewed as a thermal density matrix, what you can do is you can try to diagonalize it, right? And upon diagonalization, consider a purification that would be a precise analog of a thermophile double state that you can always do. And in this analogy that you can denote as purifying to a state that is like a square root of the density matrix, right? The energy, the analog of the energy eigenvectors are just eigenvectors of the density matrix, and the analog of these weights that you include in the thermophile double state are just square roots of the eigenvalues of the density matrix, right? So what I'm saying is that you can always do this. And in this talk, whatever I will have to say concerns a very particular situation in which we consider a 1+1 dimensional quantum mechanical system on the lattice. So this is a constant time slice of such a system that is like a spatial lattice. And we consider a situation in which we have two intervals like A and B. And we'll be concerned with the density matrices that are obtained as a partial trace of the complement of AB of the vacuum state, say, right? Now, if somebody gives you such a density matrix, what you can do is you can construct a canonical purification that will be a thermophile double purification. So like the square root of the density matrix purification, right? And such a purification would involve A, B, clearly, right? Because this is what we start with, but there would be also A prime and B prime, right? That would be the manifestation of A and B in the other copy of the system that we take, right? So this is the basis of the basis for the reflected entropy, the starting point of the reflected entropy, right? So we consider a purification of the density matrix in A and B to be a pure state in A prime, B, and B prime. The partial trace over these auxiliary degrees of freedom gives us the original density matrix. But what we'll be doing is we'll be taking a partial trace not with respect to A prime, B prime, but actually with respect to B and B prime, or alternatively with respect to A and A prime, right? It's a pure state. It's not going to matter for the purpose of von Neumann entropy. And we calculate the von Neumann entropy of this density matrix in A and A prime. And this is basically the definition of the reflected entropy. So what we do is like we take a reduced density matrix, we do the canonical purification, we cut the system, we bipartition the system along this cut, and we calculate the von Neumann entropy with respect to this cut, right? This is the definition of the reflected entropy. So if you go back to the thermophile double state, right, you might consider, well, maybe I don't have to discuss it actually. That's fine. And then the entanglement of purification actually is defined very similarly, but now there's going to be many purifications that correspond to the same density matrix, and they all differ by an action of a unitary that has only non-trivial support on A prime and B prime. So what we do is we define a state that has arbitrary unitary acting on A prime and B prime, right? It doesn't change the reduced density matrix in A and B that is physical that we start with. And we calculate, again, the von Neumann entropy with respect to A prime, B prime decomposition, and we minimize over these unitaries, right? So reflected entropy is a simpler quantity to consider because it does not require minimization over unitaries. The entanglement of purification is a nicer quantity in the sense that it's been considered in the context by the quantum information community actually for a long time by now. However, it's more tricky to operate with in quantum field theory because you have to minimize over unitaries in general large Hilbert spaces. Not an easy task to do. Okay, so what I will have to tell you is basically explorations of these two quantities, reflected entropy and entanglement of purification, in 1+1 dimensional conformal field theories on the lattice. So this brings me to goals. So this is basically what I said. And we're looking at 1+1 dimensional conformal field theories on the lattice in their vacuum state because that's basically the simplest thing that you can think of. Also because in conformal field theories you don't get like any additional scales, right? So basically this problem of two intervals in conformal field theory on a 1+1 dimensional conformal field theory on a lattice is going to be parameterized by the size of one interval, WA, the size of the other interval, WB, as well as the separation between them, right? So this is the specification of the problem in conformal field theory, and we also need to specify what is the lattice spacing, right? So you're going to have basically 4-dimensional numbers from which you can specify 3-dimensionless combinations. And if you calculate entanglement of purification, it's going to be some function of these 3-dimensionless combinations. And if it's UV finite, you know that the cutoff is going to drop. And as a result, in this case, it would be the function of just like, WA over WB and WA over D. But if you consider, for example, the separation that is 0, it turns out that this answer is not UV finite, and then the cutoff enters, and then the situation becomes a bit more complicated. So anyway, so this setup is actually still challenging. And the reason for it is that in general, continuum limit requires taking large subsystems, and large subsystems leads to large Hilbert spaces, right? Because the size of the Hilbert space in quantum many-body systems scales exponentially with the system size, right? And to counter this, we adopted two strategies, one in each paper. So in the first paper, we consider 3 conformal field theories for which reduced density matrices are Gaussian. And when we consider Gaussian states, actually, despite the fact that the dimension of the Hilbert space is, can be very large, Gaussian states are very special states in the full Hilbert space that are specified by basically polynomially growing number of coefficients with the system size, right? So they're easy to operate with, and as a result, it's easy, to obtain reduced density matrices, to purify a Gaussian state to Gaussian reduced density matrix to a Gaussian pure state, and to for example minimize over different Gaussian unitaries as entanglement of purification requires. So like that's the first strategy. And the other strategy, when you have a complicated problem, the problem often simplifies if you introduce a small parameter. So we want to recognize a small parameter here, and it turns out that a nice small parameter is going to be a ratio between the size of each interval and the distance between them. So when these intervals are taken very far away, then it is natural to expect that the description of the system is going to simplify, and we will see that it is really the case. Yeah. So this is basically all that I had to say regarding introduction. So if you have like any questions about the basics, like please go ahead and ask them now. Okay. So let me move on. So in the following slides, I want to tell you a bit about the work with Hugo Camargo, Lucas Hack, Alexander Jan, Tadashi Takaragi, and Vint. This paper actually considers several quantities, like it looks at mutual information in the massless limit of free boson theory. It looks at entanglement of purification in several situations, and it looks at complexity of purification, which is another quantity. And here I just single out like a very teeny tiny fraction of the material that we cover in the paper for the coherence of this talk. So I will be looking at the Gaussian studies for entanglement of purification for two adjacent intervals. So the setup are free conformal field theories. I will have in mind two free quantum field theories. The first one is the free boson theory. If we take a free boson Hamiltonian and discretize on a lattice, we have basically this quadratic many-body Hamiltonian, whose vacuum state is entirely specified in terms of covariance matrix, which is a matrix of quadratic correlations between fundamental variables. So a correlation between pi and pi on different lattice sites, phi and phi on different lattice sites, and cross correlations. The only subtlety, and this is why here we look at basically adjacent intervals, is that in this theory, there is a problem in taking the exact massless limit. And the reason for it is that if we take the exact massless limit, then this leads to long-range correlations in the systems that are incompatible with cluster decomposition principle, as a result of which there are two possibilities to deal with it. One is to compactify the bosonic field, that is like to make this bosonic variable run not over all real values, but only over some range. And if one does it, then one loses Gaussianity per se. In a sense, one can still use Gaussian techniques, but it's more involved. That's not what I wanted to do. And the other possibility is to introduce some residual mass and try to see how quantities scale as the mass is lowered. And if one can see that the limit when mass goes to 0 is well defined, or there is some simple scaling with the mass, then one is in business. And this is the strategy that we adopted. That is, we're going to consider we consider a free boson Hamiltonian on a lattice with a tiny but non-zero mass, and we just want to see what happens as the mass is taken to 0. Like always non-zero, but like it's subsequently smaller and smaller. So the benefit of this is that, of course, the reduced density matrices are Gaussian, and and the canonical purifications are Gaussian. And when one seeks for entanglement of purification, when one has to act with unitaries on these auxiliary Hilbert spaces, one can also take them to be Gaussian. But this is an assumption. I mean, of course, one may imagine that one purifies Gaussian states to non-Gaussian states in an enlarged Hilbert space. Over here, we're going to consider purifications of Gaussian states that are Gaussian. and we'll also optimize only over Gaussian purifications when we act with a unitary on auxiliary factors. And the good thing about Gaussianity is that Gaussianity makes size of matrices polynomial in the subsystem size, and this leads to efficient manipulations. And it's therefore much easier to reach continuum limit than one may have expected. Similarly, one can also consider a free fermion Gaussian setup. And due to Jordan-Wigner mapping, the free fermion Gaussian setup will encode adjacent intervals in the Ising CFT vacuum, right? So like that's an alternative scenario to consider Ising CFT. If the two intervals are adjacent to each other, then it turns out that Jordan-Wigner mapping allows us to represent the reduced density matrix as a Gaussian state, and then one can apply the Gaussian technology to purify it, etc., etc. One subtle thing that is required to mention is that for non-adjacent intervals, the situation is not so rosy. That is, for the Ising model, non-adjacent intervals are non-Gaussian. And the reason for it is that the Jordan-Wigner mapping is non-local because of this Jordan-Wigner string. So as a result, when one considers two intervals in the spin variables, then this designation of two intervals in spin variables is vastly different than designation of two intervals in fermionic variables, because in order to go from one to the other, one needs a Jordan-Wigner string that stretches between the two intervals. That is, and such a Jordan-Wigner string that stretches between two intervals is not included in each other description, and therefore, like the Jordan-Wigner mapping is incompatible with the disconnected intervals. That is, like it gives rise to a different notion of reduced density matrix. In particular, for experts, it gets rid of the sigma field from the spectrum, so dimension 1/8 operator from the spectrum.
Sorry, you meant that if I treat the fermion field theory and look into this and look into two disconnected intervals, that disconnected the reduced density matrix is not Gaussian in the fermion fields, but
exactly.
But does it still look? Oh, okay. Maybe in terms of spin variables, there's not really clear notion of Gaussianity.
That's the point. Yes, exactly. So what I'm saying is that you can consider a reduced density. You can construct the density matrix here for two disjoint intervals, and in fact we did it for the second part of the talk that I will show you in a few secs. But it's not the one for which like the free fermion variables are the most useful one. So basically, what I have in mind, maybe I can try to annotate here, right? When we have when we have like these two intervals, so like that's one interval, like this is the other interval. When in order to go from one description to the other, we have to invoke the Jordan-Wigner transformation, and this is the definition of the Jordan-Wigner transformation. So S plus is a combination of Pauli matrices, and F are the fermionic variables. Mm-hmm. So what I'm saying is that this is basically a fermionic string operator. So that means basically that it's an operator that extends, like say from here, it extends all the way to there, right? So what I'm saying is that this is an operator that has a support outside two intervals, and as a result, in order to specify its expectation value, you have to have access to whatever is happening outside the two intervals, and this is the reason why the locality notion for fermions and for spins is different.
Right.
And also, like the other aspect is that the Ising model is not really a theory of free fermions. This Jordan-Wigner mapping introduces like this Jordan-Wigner string in the Hamiltonian.
Okay.
And when you calculate the entanglement entropy, there are these there are different spin structures that you can consider for your calculation of entanglement entropy, right? And the Ising model is going to correspond to one, and the free fermion theory is going to correspond to the other.
Right. But can I consider fermions without using the Jordan-Wigner map, without referring to the notion of locality of these spins? Would
Yes,
that?
you can. You might. The only problem that you're going to encounter is that it's not going to be necessarily a CFT that has a modularly invariant partition function.
Okay, okay.
But if you are happy to live with it, then it's fine. So in particular, we're gonna just in some of the later calculations, we're just gonna consider free Gaussian free fermionic calculations
I see.
that are gonna correspond just to a free Dirac fermion CFT, in which there is no sigma operator.
Okay, I see.
Okay. Yeah. Thanks for the questions.
Thank you.
So anyway, so this is what we did. So like we do Gaussian calculations. I'm not gonna go into technical details. We elaborate about these technical details in the original paper. So we have like two intervals, like we have like A and B. These two intervals have different sizes, and we take the distance between them to be 0. So like they're really adjacent. And we consider a purification, and we minimize over different purifications. And here are our data points. So what we do is like we take a ratio of like the length of the A interval to the total length of the A and B interval, right? Like the joint, and we plot it. I mean, we plot the entanglement of purification as a function of this variable, and this is what we get. And the dashed curve is a fit of an analytic formula for bosons of C over 6, so C equal to 1, log of WA, WB over WA plus WB times delta, where delta is the UV cutoff. And as you see, like this fit is extremely good. Here, we do the calculation that can be thought in two ways. Like on one way, this can be thought as an Ising conformal field theory calculation. On the other, it can be thought as just a free fermion calculation. And there is no distinction between these intervals are joined together. And as a result, like this Jordan-Wigner business does not apply there. And you see that, again, the data points lie extremely well on a curve that is C over 6, with C equal 1/2. As for free fermions, log of the same ratio, right? So basically, the ab initio numerical calculation that relies only on Gaussian states is capable of producing results that it turns out reproduce continuous predictions for entanglement of purification. And I will come to this later in my talk.
Does the coefficient of the log has anything to do with the central charge? Is it really C over 6 there?
Yes, and I'll talk about it in one of my last transparencies. Yes. So over here, the only thing that we did is we did numerics. We consider a subsystem of a size of several sites, like several sites in A, several sites in B, and we consider a purification to the system that has twice as many discrete degrees of freedom. We had a numerical code that was optimizing the entanglement entropy for A prime over this bipartition for different Gaussian unitaries acting on A prime, B prime. This was a numerical procedure, and the result of this numerical procedure are these data points, like here and there. So this is the only thing that we did. And then there was an analytic formula that was derived by Tadashi earlier with collaborators using path-integral optimization that I will show later, that was predicting C over 6 log of this, this particular expression. And it turns out that our calculation that was not really making any assumptions confirmed this analytic prediction.
I see.
Yep. So it was I mean, it was an interesting cross-check because pattern optimization is not necessarily something that you take for granted. I mean, like, it's a proposal. So, I mean, it's nice that you can do lattice calculations and confirm the predictions of this proposal. That's sort of the point of this slide. So let's move on. So in the remaining 15 minutes or so, I want to tell you about something that is more general. So here, everything was Gaussian. Now I want to tell you something that I expect to be more general and to apply to any conformal field theory on the lattice that has a gap in the operator spectrum. And this is the subject of the paper that we put together with Camargo, Hackl, Jan, and Vint in February this year. So again, the idea is to introduce a small parameter, and the small parameter is going to simplify our life. So again, we look at the situation in which we are in a vacuum of a conformal field theory on a lattice. So like, this is the lattice, right? We consider the two intervals, and now these two intervals are the same. So they have like size w, and the distance between them is d, okay? And we consider a purification. Well, actually, before we consider a purification, it turns out that like there is a, as I said, like there is a UV finite quantity that one can consider that is mutual information. And it turns out that the mutual information in this large distance limit behaves in a universal way. That is, if the lattice operator, if the CFT has a gap in the operator spectrum, and the lattice operator, apart from identity, has a scaling dimension delta, then the mutual information at large separation behaves in this form. So n is the degeneracy of the operator with scaling dimension delta, because there can be more than one such operator, right? These gamma functions are some prefactor that can be derived using replica trick that depend on delta. And then the scaling here is with w over d to the power 4 delta, right? Because of this square. Okay, so like, this is the known result for long distance behavior of mutual information. And what we will be interested in is deriving or going in the direction of deriving an analogous formula for reflected entropy and entanglement of purification. So we're gonna be assuming that there's a gap in the operator spectrum, and that we are on a lattice. And when we are on the lattice, we can talk about reduced density matrices with full comfort of it, right? In quantum field theory, it's a bit problematic, right, to talk about density matrices in continuum, but on the lattice, there is nothing that prevents you from doing so. And the key insight of our consideration is that when we look at the systems that are infinitely far away, then the density matrix in A does not know about what's happening in. What I'm saying is that like the systems A and B completely decouple, right? Like, if they're infinitely far away, that's basically the cluster decomposition in quantum field theory. So when we look at the density matrix for A union B, and one can imagine that there's going to be higher corrections involving powers of epsilon squared and higher powers of epsilon, where epsilon is this variable. So what I'm saying, the only thing that I'm trying to say is that there is a well-defined perturbative expansion of the density matrix around the situation in which it factorizes between A and B. And one can work out to linear or quadratic order in this parameter epsilon that is a parameter appearing in the correlation function. And one can try to construct canonical purification or entanglement of purification in a perturbative expansion with respect to this epsilon. And the key insight for us came from considerations of small subsystems. So we'll be looking at a situation in which the system consists of infinitely many spins on a line However, the subsystem A is one spin, and subsystem B is another spin far away from each other. And it turns out that one can derive analytically the form of the density matrix for A union B, where A being one spin, B being the other spin. And this density matrix has a very simple form and is given in, like with analytic expressions. So like this D, E, C are, some numbers that we know in a closed form. These diagonal part of the density matrix correspond to these systems, so being decoupled in the infinite distance limit. And then there's a correction, and this correction is precisely the correction that cares about dimension 1/8 correlator with each operator inserted in in the respective subsystem. And this operator, the dimension 1/8 operator in the Ising model in the conventions that we use correspond to sigma x. And you see here that these off-diagonal corrections are nothing else than sigma x's. So this is the density matrix that is written in the basis, up, down, up, and so on and so on and so forth. So having such a density matrix, you can calculate its fundamental entropy using a standard formula, right? So you basically diagonalize it. The eigenvalues are mu's. This matrix is 4x4 matrix, so there's going to be 4 eigenvalues. We denote them by mu 1, 2, and mu 3, 4. And the expression for the fundamental entropy is this. And once you plug these eigenvalues into the exact expression, and you isolate the part of the SAB that scales with the separation between the systems, this gives rise to the mutual information. And the mutual information is some prefactor that we have in a closed form times this epsilon, and epsilon is this quantity squared. And now if you compare to the exact expectation for the mutual information, you see the factor of epsilon squared appearing that is exact. I mean, this is what we wanted to get. And the prefactor here, actually, the numerical prefactor, as compared to what you get from analytics for delta equal 1/8 and n equal to 1, is off just by 3.6% from the exact value. So the lesson from this is that it might happen that for a small subsystem at large separation, the approximation of continuum result for quantities such as mutual information is actually quite good. So motivated by this, the first step in our analysis was to look at reflected entropy and entanglement of purification when we consider a subsystem that consists of two separated from each other spins, and this allowed us to do calculations in an analytic way. So again, the fact that there's a small parameter in the problem that is this epsilon, so basically the ratio of W over D, allows us to seek for purification of our density matrix in a perturbative form, perturbative in epsilon delta. And when I say perturbative, I do not want to imply Gaussianity or anything like this. The system can be as no Gaussian as possible. However, it is the separation between the two subsystems that allows us to do the analysis. So starting with such a density matrix, we can seek for a purification, to the density matrix that does not depend on epsilon, that is linear to epsilon, that has a quadratic dependence on epsilon, and so on and so forth. And it turns out that the piece that does not depend on epsilon is very simple. This is the purification that one has to consider. and then one can proceed to the quadratic order here, and one can again consider a decomposition of the system into A prime and B prime, and calculate reduced density matrix in A prime, and it turns out that as a result, like, one gets eigenvalues, and these eigenvalues basically have an epsilon, depend on epsilon as epsilon squared, with some prefactors. These prefactors are denoted by alpha. There is like the alpha tot, which is a sum of like all alpha j's. And the most important thing is that in principle, you can imagine that this total alpha is going to be 0, and all alpha j's are going to be 0, and then the first non-trivial contribution is going to come from higher order. However, this turned out not to be the case, and when doing the explicit calculation, we found out that the SAA prime is going to be given by epsilon squared log of epsilon plus subleading term without the log. So this log for epsilon that is close to 0 is going to give us an enhancement. So this is going to be the leading scaling, and this alpha coefficient depends on parameters in the purification that are here denoted by x2, x12, and so on and so forth, following notation from the paper. And this is, as you see, like this is basically an analytic expression that is a quadratic polynomial in these x parameters. And what we have to do is we have to optimize over these x's if we want to define entanglement of purification. And optimization of these x parameters that define purification are nothing else than optimization over this unitary that acts on A prime, B prime. So because it's a quadratic expression, I mean, finding the minimum is really trivial, and we can do this analytically, and we find the value of this parameter alpha at a minimum to be given by this formula. And similarly, one can proceed in a numerical way. That is, one can play precisely the same game for bigger subsystems, and construct density matrices, consider purifications now, not necessarily perturbative ones, like just consider the general purifications, do the optimization. And this is what we did for the Ising spins. And for the Ising spins, we look at subsystems of the size one side and subsystems of the size of two sides. And we got the resulting expression that was not too different from each other, and like W equal 3 delta. So for subsystems of 3 sides, the optimization was actually too challenging to perform in the Ising spin language. But looking at the mutual information, we already know that W equal delta. So for 1 plus 1 side, the result for the mutual information is very close to the continuum limit. And W equal 2 actually agrees basically almost exactly with the continuum limit. So this is what we know from mutual information, and we expect similar structure is going to hold for entanglement of purification, although of course we are in no position to verify it. We also play the game for free fermions. So for free fermions, it's much easier to do calculations for larger subsystems. So we consider 1 plus 1, 2 plus 2, and 3 plus 3 sites. And we already see that for 3 plus 3 sites, the mutual information is very close to the continuum prediction. And for entanglement of purification, well, we also expect that the 3-side prediction in this case is close to the continuum limit. And based on this, actually, we came up with a conjecture that says that long-distance behavior of entanglement of purification in a generic 1 plus 1 dimensional conformal field theory on a lattice, with conformal field theory having a gap in the operator spectrum, is going to scale like the mutual information enhanced by a logarithm of the ratio of the distance to the subsystem's size. Right. So basically, this is a new relation. I mean, this looks like a new relation with respect to the mutual information, because mutual information only scales in a parallel way, and therefore is is challenging. One can consider a simple quantity that is reflected entropy, and it turns out that for reflected entropy, actually one can prove that the scaling of reflected entropy is precisely of that form. That is, it's like the mutual information times a logarithmic enhancement in distance. So our analysis allows us to prove this on a lattice for conformal field theories with a gap on operator spectrum. And well, this is what we did in our papers. That is like to find this parallel logarithmic scaling of entanglement entropy and mutual and reflected literature is related to the question that Janet asked earlier, which is these two plots for entanglement of purification obtained using Gaussian techniques for two adjacent intervals. And it turns out that the results that we derived using, without any assumptions, using Gaussian numerics, agree with an analytic formula derived using path-integral optimization in 2018 by Tsaputa, Miyagi, Takayanagi, and Umemoto. So this is the prediction of the analytic formula is C over 6 log of WA WB over WA plus WB times delta. Delta is the UV cutoff. And our numerical results, or to our more general results, it turns out that in two papers in 2020, Orazio Cassini and Pablo Bueno consider numerical studies of reflected entropy at for two intervals in Gaussian theories. And after we put our paper online, the first version of our paper online, they pointed out that they actually observed the logarithmic scaling that we also see in entanglement of purification. And this also motivated us to try to seek for a proof of this scaling. And what I'm showing to you here are our results for reflected entropy. So for free fermion systems where we can compare with Bueno and Cassini. So these are our data points for interval for subsystems of 3 plus 3 sites. And this is the fit to their numerical data. And you see that this fits agree rather well. Like one more thing that you see on this plot, and that's going to be the end of my talk, is that if you compare entanglement of purification and reflected entropy, you know that in holography, if both statements are correct, that is, like if the statement by Takayanagi et al. And the statement by Faulkner et al. Are correct, then there should be a factor of 2 that relates them. However, we see here that for free fermionic CFT, this is not really the case, that entanglement of purification is 1/2 of the reflected entropy. The relation between these two is much more intricate. So if the holographic conjectures are correct, then they must be applicable only to a particular class of states that are holographically realized, not the class of states that are seen in, not necessarily to the class of states that are probed by free theories. So let me summarize. So today I talked about 2 papers that appeared in the course of the past 6 months. One in which we utilized Gaussian framework to calculate entanglement of purification for free fermions and free bosons, and the other one in which we introduced the small parameter to the same endeavor, that is to studies of entanglement of purification and reflected entropy, which is the separation between 2 intervals. So entanglement of purification and reflected entropy are, I would say, little understood quantities in quantum field theory, with interest in them triggered by ADS CFT. And the simplest setup that one can consider that at the same time is non-trivial is a vacuum of a 2-dimensional conformal field theory and 2 intervals that are separated by some distance d and have size WA and WB. In our works, in the 2 papers that I described, we adopted 2 strategies. The first strategy was to consider Gaussian techniques to study adjacent intervals. And the other strategy is treating the separation between intervals as a small parameter that allowed us to seek for purifications perturbatively in the small parameter. For adjacent intervals, our Gaussian numerics confirmed the prediction of the path integral optimization, which is nice because path integral optimization is not something that is derived, it's a proposal. So the fact that we are able ab initio to rederive predictions of this proposal strengthens this proposal. And for large separations, we proved on a lattice that reflected entropy behaves like mutual information enhanced by a logarithm of a distance. And such a scaling was observed earlier by Bueno and Cassini, and here we use lattice techniques to prove it. And for entanglement of purification, we provided numerical indications that the same scaling holds, although we were not really able to prove it. We just analyzed it example by example. So that's all that I wanted to share with you, and thank you very much for your attention and staying with me.
Oh, thank you. Are there any other questions from the audience? Okay, let me stop the recording. I have a few more questions actually.